Okay, so welcome to Network Security lecture number 5. So where did we stop last time? So we talked about cross-site communication, especially the challenge that we have if we have several branches of our network that should be connected somehow, and also some remote workers joining in from any random IP address, probably at home, probably at the customer side, traveling around. So here we might have some fixed IP addresses that are known, but this is quite generically very random. So it can be at home, it can be through smartphone, and then with a new IP address. And what we want to achieve is that these networks should be connected in a way so that if here's some kind of printer, the machine here should be able to print, or if we have any kind of services in the network available, file server, email server, printers, I don't know, any kind of repositories, any kind of services running, should be available from these branches, from these networks. But this is the evil internet in the middle, and here are evil persons, and they should not be able to access that network. So how can we connect to those domains? Approach number 1, with building own lines, obviously is not really doable. Let's say for the stationary sites, that might work if they are locally close. That's sometimes also happening, but quite rarely. But typically, especially the home office workers, not achievable to be put into the network as well. So what we need is some kind of approach that allows us to use the internet that we have available and to put, one moment. Yeah, and somehow to use the option to use the internet, although there's lots of evil involved, and connect those machines. Another approach would be just to leave holes open so that our remote worker can connect to our network branch, but that also is not a right way. So we learned already through the firewall configuration how we can allow incoming traffic from various IP addresses and put a filter on which IP addresses are allowed to send us messages to our internal network. But because we don't know the IP address of the home office worker that changes frequently, it would be quite an effort to always be up to date and to allow only that specific IP address that is currently active of the home office worker, and leave out the IP address of the evil persons that want to also, I don't know, misuse our services, access our file server. So that should also not be the way. So what we have instead is still we use the internet, but what we do is we create virtual lines. So we still want the lines, but we want to have virtual lines that establish a connection between, let's say, a network, and this virtual line has very nice properties. So what it should be encrypted, it should be authenticated, so that we know, okay, this is really network A or home office worker B, and this is our local branch with our printer and file server and so on. So we create a virtual network line which has this nice properties, encrypted. It's integer, or how's it? So that integrity is provided, authenticated, so that we know who's connected. So and how is this created? The machine itself creates a new kind of virtual network interface. And this virtual network interface is attached to a VPN software that's running on the machine. And any packet that is coming in is run through the VPN software. The nice security properties are added, so it's encrypted, integrity is provided, and it is sent on this dedicated virtual line to a dedicated endpoint. because one endpoint here and this VPN software is another endpoint. They have established a secure tunnel, meaning that everything that passes through has this nice properties, encrypted, integrity, authentication, and we can put any kind of packets that are destined to reach to network B, and any packet that is sent to this virtual network interface that goes through the VPN software eventually ends up popping out at this, so basically that tunnel endpoint is where it's coming out. This is also a host, it's receiving that packet and it forwards it on internally in the local branch. So, this is the idea, how it can be done. And the question will be, what is the task of the VPN software? How do we achieve this nice security properties so that all traffic is encrypted, authenticated, integer? And then the benefit is that any kind of application sending packets doesn't have to deal with it. So how to make it all secure? It's open for any kind of application. You can access the printer, you can use your regular printer software to use the printer up here. You can use your regular, I don't know, file access tool to access the file server at the local branch B. They are unaware of our host being remote to the local branch B. So this is the nice way how it can be done. Basically, what you always try to achieve in networking is that you don't have to know how internally it's done. So you have this layering, and if you have the application layer here, so app, and then you hand over your messages. Basically, here will be some kind of network wrapper, let's say VPN, that uses then TCP also, and that uses IP, and that uses the link layer. So the application doesn't have to know how the packets are actually delivered to B and there a specific host and a specific application. So it doesn't have to know. It just focuses on its own tasks. So the application, like printing protocol, and also the IP network doesn't have to know what's inside of these packets. It has just to deliver the packets to B, so that they are to the endpoint of the VPN tunnel. And the focus in adding this new functionality for secure communication is just in this single layer where we have to focus and have to look what information we need to provide so that the functionality that we want is achieved. So, what is the task of the VPN software? So what it has to do is, okay, so this is now when the message was received. So basically this is the sending part. So it's adding some kind of header to the VPN of the VPN protocol. It's encrypting it and sending it on its way. And this is what is visible to the internet. So it's an encrypted message destined to B. And on the recipient side, the encrypted message is received and it's delivered to the VPN software. The VPN software that can decrypt it, can verify the integrity, can verify the authenticity of the sender, and then it is passed on. So basically, it's received by the virtual network interface and it's sent out through a regular network interface. So this is the main idea of a virtual private network. So if we have a look at how it looks like, so then we have two internal networks, let's say with these IP addresses, 1200, with a subnet mask of 16 bits, and 1300 with also subnet mask of 16 bits. There's an IP address of the firewall on this side and an external firewall IP address, and the same, we have a public IP address on firewall A, and in between we have lots of malicious internet activity. And what we do is basically the virtual interface, all messages sent to this IP address or this network interface is then basically encapsulated and sent on its way through this tunnel and received over the other IP address that is also the firewall is passing through messages, but only if they are authenticated, if they are integer, and we can decrypt it. So, okay, so this is the main idea. And in between, again, what is visible? We see an encrypted message that is coming from A, and so it's coming from this public IP address, and it's going to this public IP address, and more we don't see. And any malicious attacker can try to, I mean, it cannot decrypt it, it doesn't have the keys, it cannot modify bits, otherwise they would be identified as modified, as integrity guarantees that any modification is detected. It's not hindering it, it cannot prohibit it, it cannot disable it. So modifications can happen, but then they are detected and then the packet is discarded. And we also need authentication to really see that the sender is from branch A and it's sending messages to the branch B. Okay, what might the firewall routing table at site A look like in the network shown above if we have this kind of IP addresses? Ah, yes. 9? 9, okay. So what you do is basically all, so anyway, all internal firewall traffic here is anyway prohibited, is anyway permitted. So it's happening. And now we can think of what kind of traffic you want to allow from firewall A. So first of all, any traffic that goes out. So we had this example of stateful firewalls. So everything that goes out should be fine. Everything that goes in should be only with the state established and or coming from yeah, it depends on how we see it, whether it comes from this IP address. And also, of course, anything, so we don't even have to make sure at our firewall to be aware of which IP addresses we have. We just delegate the task to resolve which IP addresses are valid and accepted as senders in our direction based on our, so the VPN network and software determines who's authenticated and is allowed to send messages to us. So let's say in the beginning, every message, and so this is any message that is arriving at this specific IP address, internal one. No, it's our. So basically, what we allow is we allow traffic from outside to 10.8.0.1. So if it's not of the state established, let's say a website lookup, but it's coming from outside, then it should be passed to the VPN software, and then it should be checked. Of course, only if it's addressed, but it should be then checked whether it's a valid VPN message, and we have a valid sender that we previously established a connection to, so that it is allowed to send us messages. Okay. So there are many possibilities to realize tunnels or VPNs. What they differ in. sorry. Ah, no, yeah. Is at which layer it happens. So is it layer 2 or layer 3? Because we can have, so if layer 2 is the one-hop communication, then we can have a virtual link basically through the internet, which is invisible basically for the participants. For the participants in the VPN, it just looks like as it is a regular link. So any kind of ARP request or service lookup is directly passed on, and it's just acting as a replacement of a direct link of a cable. But it can be also an explicit, so layer 3 firewall, a virtual private network, where you dedicatedly have to say, I want to contact this node, so that it forwards it on to that other node in the internet. And then it's over layer 3, basically. So it's the question, is it implicit, so is it hidden, this VPN connection, and you just don't see it in the network. Even if you scan the network, you send out ping requests, or you just have a look at what other network participants are in your network, and you flood the network, let's say with an ARP message, then it's automatically also flooded over. Or do you have to explicitly tell, I want to address, I don't know, this IP address B, and my default route in addressing hosts that are not in my direct neighborhood, in my one-hop network, is this is my router that should take care of handling my packets to forward them to the right place, and this router and then knows in its forwarding table that it has to send this message using the VPN encryption and everything to that other router, where it's then forwarded in the local branch. So, yeah, what else are we having differences in? Can we only communicate to a single remote station or to multiple remote stations? So can we communicate to the network and don't have to know in advance who our communication partners are, or do we have to know it dedicatedly, and then we have to only establish a connection to that single station? Yeah, let's have a look at how the differences between the various layers. So because up to now we were just assuming that we have the station and it has its virtual private network interface, and any kind of message that goes in and is to be forwarded through this interface sends the message over the evil internet, and then basically is arriving at the other branch. And the packets that we sent were IP packets that were put in some kind of capsule. So this is our IP packet, and all this additional encryption was added, and authentication and so on. Okay. Yes, and in this case, that would be. So the question is, what is this encapsulation? Because you can send the IP packet directly. So this is an IP packet that you send. So it's basically already on the network layer, on layer 3, where you send IP packets, and you can put it in various kind of envelopes. There are dedicated envelopes for VPN, but you can also put it in other envelopes, such as a DNS packet or so. So you can also put it just in another protocol. So then it's called IP over DNS tunnel or so. Or you can also put IP packets in HTTP, or you can put so you can put any kind of IP packets in other application layer protocols, and the recipient is then an application that knows, okay, in this DNS message, for example, is an IP packet embedded that I need to process. So it's not really, so if you, for example, put it in DNS, then you don't pass it on to the DNS server, but you pass it on to IP over DNS server which knows that it is a has specific contents, that message. We will see what the benefits of this are, but just to highlight one of the benefits, there are some few popular protocols that are typically always enabled. So typically HTTP traffic is not blocked, typically DNS traffic is not blocked. And if you put in IP packets in that, then you can pass on information in those as well and can use the benefits of this application layer protocol while using it for a different application. But, so this would be the IP, the layer 3 tunnel. But we could also send Ethernet frames. They're different. I mean, here we address per IP address. So we have the IP destination address. But we could also use Ethernet as a lower layer. Ethernet itself is built differently. It has, let's say it starts with the destination MAC address, with the source MAC address, with the type, typically telling which higher layer protocol it should be passed on, then the data, and then there's the cyclic redundancy check to check for bit errors. And this you can also send through the VPN tunnel. And the idea is that by sending this kind of packets, let's say you have, so what is the layer 2 actually doing? This is the one-hop communication. And if this is your host, it might have a Wi-Fi access, but it can also have an additional VPN link layer. And this link is more clever and it can establish basically another encrypted, authenticated communication to another host, which is, let's say, behind the firewall. So these are the two branches. And because the VPN is more clever, it can communicate to the VPN service at the other branch side. They establish the connection to each other so that the firewall passes on their communication, so this is possible. And then you can put in any kind of Ethernet packets that you think you send over. You think this is some Ethernet network card, but actually it's not. And all messages of this type are passed on to this node. So to both hosts, it looks like they are really directly connected, and they can easily exchange frames between each other as if they would be in the same network, as if they would be connected by the same cable. Okay, so both has benefits. If you put it in layer 2, this is really then to your network, it seems like they are connected in the same. So you can run your layer 2 protocols basically. You can search for services, you can broadcast address resolution protocols. So who has this IP address? Please give me the MAC address. And then if you have the MAC address, you can send through the VPN directly a message. So it's really more connecting the two networks on a lower level. And in layer 3, you can use various application layer protocols where you just embed your IP packets, but you actively have to address who are your IP recipients. Okay, so basically the layer 2 tunnel and the layer 3 tunnel tell what inside the tunnel packets are being transmitted. So can I send my layer 2 information, such as Ethernet packets, such as ARP requests to resolve IP addresses? Or is it that I only can put in IP addresses which have some application layer on top? So, and this is basically what's inside. So inside we can have IP or some Ethernet. So, but the question is, what is this? Okay, so if you want to set up a tunnel between two sites A and B, or what kind of connection do you send the encrypted packets from A to B? What kind of wrapper do you put your encrypted packets in? Would you put your packets in UDP or TCP. I mean, this is if you put, let's say, this is some kind of protocol. So what you actually have then, if you look at the layering, so we have the link layer, we have the IP layer, then we have the TCP or UDP, yeah, and then you have actually your VPN that acts as a link layer or as a IP, yeah, actually as a link layer. So basically this creates a false new link layer, so that you can put in IP packets. Yeah, that's what we talked about previously. So whether it's a layer 2 or 3 tunnel, whether you put in here Ethernet or IP, that's basically converged and is a new application layer protocol that is using TCP and sending the packets encrypted over IP. So the question is, which transport layer protocol would you use? So would you use TCP or UDP? Because on top of here, again, here we have, let's say if we picked IP, then we have again TCP and UDP. And let's say we want to have some HTTP request to the other branch. Yes?
I would say in general, it depends on what's more suitable for the application that's running on top. In this case, HTTP, I would say TCP. Yes.
Okay, let's see. So HTTP uses TCP here and TCP here again. Okay, that's good. Good point. So, I mean, TCP offers reliable data transfer. It orders the packets correctly, and it asks for resending the packets if they have not been received. Let's say a packet gets lost. Which of the two TCPs will get active? So if I mean, this is a very large packet, so we have 8 layers on top of each other. And one physical packet really gets lost. Which of the two TCP implementations will react and ask for a resend?
I would say the left one, the HTTP.
Why is that? So when is TCP asking for a resend? If a timeout occurs, and the timeout is for both exactly the same. Actually, both will ask for a resend.
Right, yeah.
And then basically at this layer there's a resend, and at this layer there's a resend. And then you have received the same message, maybe, I'm not sure which you received then. Yeah, both. You received basically this, what was previously lost, as well as this, what was the HTTP request, what was also lost. So actually, TCP has all these nice benefits. UDP doesn't have that, but it's sufficient to have it once, because if you have it twice, then there might be problems, especially through double resending, through reorder issues. So if, let's say, it's just confusing because both TCPs have then an order in which the packets arrive, and if, let's say, various issues can happen that cause for an additional trouble that is already handled by the first TCP. So better to use UDP, because TCP assumes that the underlying network layer is unreliable. So it's fine that we use here UDP, so that we just have one TCP in action. Okay, yeah, what else can happen? Assume TCP data stream is passing through TCP-based tunnel. Then we have also this additive increase, multiplicative decrease, congestion control, that's as well. So if there's somewhere congestion, and both adapt to it themselves, then both might reduce the transmission speed, although one should be sufficient, so it can really have less throughput at the end. So always use UDP if because the higher layer, so the application layer protocols, they already decide do they select TCP or UDP according to their needs. Then the IP packet is created based on this, and that is sent over UDP-based VPN to the recipient, and that is a better combination. So, have you already installed some some VPN tunnel solutions before? Any examples? Yes, yes. Yeah, OpenVPN is very nice. So it's can tunnel over both. It's very flexible. You can also set it up at home and so on. So it's easy to configure. I also have one so that I can connect to my network at home. So it's quite convenient. But there are also other elements, other options how this can be done. IPsec is an extension to IP. Yeah, it's above IP, below TCP. It's a little bit complicated. Then there's a specific application layer protocol tunnels, such as IP packets over SSH. So this is an application layer protocol, or secure socket layer, transport layer security, encrypted TCP connections. So actually this is the newer name. TLS is the new version. So there you have dedicated new applications that place themselves somewhere in this network stack. Or they are also more on the lower layers. Point-to-point tunneling protocol. This is what sometimes in the modem or in really login setups are created, where you don't want to connect networks, but more just one device to a network. We will have a look at how this can be done. But one example I wanted to showcase to you, DNS tunneling. So what the message of this slide is that there are various layers where you can embed your IP packets in. You can put it in an application layer. So it's SSH is really just an application layer. It's above IP, it's above TCP, it's the new application layer. You can put it, TLS is a replacement for it's below TCP and above IP, so it's somewhere in between. So you can have various positions where you place them. At the end, it doesn't matter at which layer you put them. What you have is you have IP addresses that you put in a new envelope, and on that specific layer you send it over to the other site. And in between, the envelope cannot be broken, it cannot be decrypted. If it changed, then it's obvious, and the envelope also contains an authentication telling from which party the message comes. So I want to showcase you an example, DNS tunneling. What you can, for example, also do is to have your stack. You have your link layer, you have IP, you have UDP, and then you have DNS, domain name service. Basically, this is where you have a domain. I don't know, you want to Amazon.de, and that tells you which IP address it has. This is DNS. Yeah, you send out a simple request. Please tell me which IP address is associated to this domain name. You send it to your pre-configured DNS servers. Typically, also if you join the network in Wi-Fi or per Ethernet or so, you get an IP address via DHCP. So, and not just that, but you also are given the IP address of a DNS server, at least one. So there are also some public ones that you can configure from Google, 888, or I think also 8844. So these are some public IP addresses, DNS servers. And basically, also if you are visiting a cafe and you log into their website, to their Wi-Fi, and they ask you to fill out this, to confirm that you want to, that you accept the terms and conditions that you are allowed to join their network, their Wi-Fi. Typically, let's say there's a website called, I don't know, login Wi-Fi cafe.de, and this is what you are redirected to. If you log into the Wi-Fi, you want to open any web page, then you are redirected to this one. There you have to accept terms and conditions. Are you aware of this happening in the reality? Or also hotels. But this is not an IP address that you can resolve. So what you typically can do is you have to first resolve it. You have to find out the IP address. So, and depending on which DNS server you have in your machine configured, let's say you send a request to Google's DNS server, and you get back, I don't know, this is the IP address that you should visit in order to visit the splash screen for logging into the Wi-Fi. And then you click yes, and then your MAC address at the cafe is enabled, and you can forward messages to the router, then the router will accept messages from you. Okay. Do you see a benefit? Let's say you have to pay for the Wi-Fi. What kind of communication is allowed before you have to pay? Yeah, you can access the login site, but before accessing the login site, yeah? Yes, you can send an IP pack, a DNS request, to one IP address that you specified. What can be put in that DNS message? And there's a there's a nice, and then you also get the response back. So in the packets in the other direction are, so what you can do is to set up a DNS server which just with not only uses and answers to DNS messages, but this is a specially prepared DNS client that wraps IP datagrams into DNS host names in a special domain. So you can put a lot of information in that DNS request. And any answer that you get can also be put in a DNS response message. So DNS has typically quite a lot of resource records. So for example, the resource record A, so let's say if we ask for Amazon.de, this is your query, and then R tells us the IP address, R tells you the IPv6 address, then you have a CNAME, common name, that tells alternative names, such as www, Amazon. The E is linking to, I don't know, some other, so these are equal. Then you have a text field, which sometimes is mandatory to fill out so that you can verify that you are allowed to send emails. You have to put in some kind of authentication info. Message exchange with what is the corresponding mail server's address. There's the state of authority, so who's allowed, so who's in charge of this domain, and so on. So there are many fields that you can fill out, and they can be quite large. So the response can be quite large. And also, if you don't have to ask just for Amazon.de, you can ask for quite a long name and subdomains and so on before you enter the actual domain that you want to address. So you can put lots of information in the query, and you can put lots of information in the response. And you can select which server should be addressed. And there are tools for that. So for example, one nice tool is called Iodine. I'm not really sure whether this IP address, this domain is still valid, but it's also on GitHub and so on. And what it does, it sets up a local VPN connection, and there you configure which DNS server you want to send your DNS requests to. And on the other side, you have to set up your DNS server with that property that it interprets all these queries based on whether there's some hidden information in it. Yeah, and if you enable that on both sides, then you can go to your hotel lobby. You are asked to basically any DNS request is permitted in order to resolve the splash screen for the Wi-Fi entrance. But you can also send any regular information that you want to send out, such as HTTP requests, put it in an IP address, IP packet, send it to the DNS server. The DNS server unfolds it, decrypts it, and resolves it, and then it sends you back the answer. And that can be basically used to have an IP over DNS tunnel. Yeah. So, and the benefit is, you can choose your own DNS server that you communicate to. Just think of if that would be not allowed, then typically you would not be able to resolve that splash screen from Wi-Fi, because many machines just have pre-configured DNS servers that they use, either based on different circumstances, and it's allowed mostly everywhere. So everybody can define the DNS server they want to communicate to, and it's almost everywhere allowed, even with restrictive firewalls, because DNS lookup is just required to typically resolve this domain names in IP addresses. Yeah, that would be an example for DNS over IP over DNS, so meaning IP over a dedicated application layer protocol. We will also later have a more detailed look at how TLS works and how IPsec works. Then we dig more into detail. Now we just typically, now in the lecture we just fly over different topics to cover them, so that we have some impression of what is all available. Okay. So this is one topic in the domain of access networks and challenges in the network that we have. So that is quite frequently used, especially TLS is always used when you visit an HTTPS website, because what HTTPS does is it verifies to whom you are connected. It establishes, so what is HTTPS? HTTPS is HTTP over TLS, and TLS does the following. First, if you visit the website, so this is the website, you retrieve the certificate telling that it is really in charge of that domain, and so basically it links the public key of the domain owner with the domain. And it also tells you lots of key parameters. So what kind of security protocols are supported. And then, because you know the domain key, you are given some key parameters. Typically, both agree on a set of selected algorithms. So, for example, which hash mechanism to use, which encryption to use, and they both derive some keys for this special session. And because you have the public key, I mean, the website can sign information so to verify that it's really in charge and has the corresponding private key. Typically in TLS, the client is not authenticated, but the website is authenticated. Then they agree on algorithms, and what they do then is to basically establish some kind of tunnel where all ingoing message is encrypted with a specific client key that is known also to the server. The messages back from the server are encrypted. There's some integrity added based on the keys that they derived, and any request and message HTTP request that is sent is encrypted integer, not authenticated. The client is not authenticated, but the server, any response from the server is authenticated. It's integer and it's also encrypted. So this is then how it's typically used, but we will go in more detail later on that. But this is also another example of how this tunneling is used. Okay, let's have a look at other topics in networking that are also challenging. And one of the challenges, so this is basically a solution to address authentication, integrity, confidentiality. And we have also the security goal of availability. And availability is not addressed here. So TLS and tunnels don't address availability. So malicious nodes can still disable, let's say, links and overload machines. And how can the evil participants overload machines? This is typically called denial of service attacks. And the main idea is that a server that is available in the network requires resources to operate. So if it's accepting a new incoming connection, so this is our server, let's say, if it's accepting a new incoming connection, let's say this is an HTTP request, then it needs to add some resources to it. It needs to maintain the TCP parameters, so sequence number and so on. It might create a cookie, I don't know, we will have a look at what cookies are. But it uses some resources. And the idea of denial of service is that you have so many incoming requests that the resources that you have available to serve valid customers, so now the green valid customer comes and wants also to access the service, and there are not no any further resources available to provide to valid customers. So for example, how many open connections can you have on a machine, on a host, let's say for TCP? What would determine the number of potential open connections that we have for TCP? Yeah, maybe TCP is a bad example because that offers us more options. But UDP, let's say UDP. So you have a service, a message comes in, the answer goes out. Or how many new connections can you establish from your machine? Yeah, that can be answered, yes. How many new connections, unique connections can you have using UDP or TCP?
Number of ports.
Yes, the number of ports, yes. And how many ports can you have? So how many bits are encoding in TCP or UDP the ports? 32. Huh? 32? Would be a little bit too much. It's 16. So it's not so much. 64,000 or so, 65,000. And then you cannot create new ports. I mean, then all of them are used and all of the sockets associated to them are used, and then you cannot answer. This is one way of having resources. Another way is storage, another way is memory, another resource is bandwidth. So you can try with a denial of service attack to consume one of these resources that are required to provide service to the customers. Which resource would you attack? Depends on which service. Any idea what could we try? Mm-hmm.
Maybe like a lookup for each port, so that reserves running.
Yeah, that's right. Then you find out which services are running, but you want to overload it. You want to consume all its resources. So the simplest one is, I mean, if the machine has a 1 gigabit per second connection to the internet, just think of examples when our website's down. Let's say you are selling some tickets that are very popular, too many people log in and send a request, and then you might exceed your bandwidth for receiving requests. Or I don't know, if your ticket system can only process 100 ticket sales or ticket customers per time unit, then if there's a flash crowd and many people are interested, then it's overloaded and the website crashes. So if you have at least, if you exceed the maximum incoming bandwidth of the recipient, then obviously valid recipients, so there will be packet loss and also packet loss at the valid recipients traffic. So that would be an option. And yeah, let's see how to best achieve this. So what strategies are there and how to counteract. So what they want to do, they want to overload the network or the system, so either or. So here typically the memory is in question for overloading the system. If the network is more the bandwidth, crash the system with systems, yeah, routing tables, permanently damaged systems. Yeah, I'm not really sure how to do that. There are ways, yes, but that requires more effort, obviously. I mean, there has been examples such as Stuxnet. That was an attack run in Iran that dedicatedly, that was some kind of worm, some kind of virus, some kind of program that tried to overload the control mechanism for some motors, for some machines, so that the things really break due to exhaustion, so physically. But now we focus only on overloading networks and systems, and I mean, this is a little bit too exotic. So how can we create, so at the attacker side, so now we are having the attacking hat on, how can we create a good denial of service attack? So what we want to do is we want to create an overload. And if you want to overload, it should be expensive for the victim and cheap for you. So we want to have minimum utilization of own resources and high impact on the victim. And it should be difficult to identify, difficult to block. So identify and block, that means it should look like valid valid customer traffic. So that if you block the malicious traffic, you cannot distinguish it from the valid traffic, and then you also block the valid traffic that the blocking side wants to avoid. Again, picking up the example with the tickets that you want to buy. Any famous musician that you favor? So if you want to buy a ticket and that's overloaded because people find that person so interesting and want to visit the concerts, typically that happens. I mean, if it's announced the ticket system will go online this morning at 10 o'clock, then the first 5 minutes it might be overloaded. So, and then it's difficult to identify what's valid traffic, valid requests, and might be potential malicious requests. So what we want to do, especially here, minimum input, maximum output. We want to have an asymmetric resource consumption. We want to give a minimum effort to cause lots of harm. that's step number one. So ideally, one resource impact from our side causes a consumption of, I don't know, 10, 100 resource consumption on the recipient side. Then we don't just want to have one impact, we want to increase our own resources. So especially that we want to increase the potential that we send out, or that of the attack that we do, so that it's not one and turns into 10 effort, but it's 1 million and it turns into 10 million effort. Yeah, and that would be of course the best if we have more resources than the victim, but that's typically not the case. So we have to deal with these two options. So, and now we are looking at options how we can achieve this asymmetric resource consumption using available protocols that any server should support. So let's have a look at some examples: SynFlood, Smurf attack, and DNS amplification. And I think especially with this, no, it was HTTP based. So there was a very nice attack recently, which had a very nice amplification factor, really great. I will also talk about it. But let's start with SYN flooding. So what is SYN flood? Where's SYN? In which protocol are you aware of the term SYN? Yes? Yes, exactly. So TCP. So typically, if you want to establish a TCP connection, there we have a TCP handshake. So we send, so this is the client, this is the server. We send a SYN telling we want to communicate with you. And this will be actually our sequence number. Sequence number starts with X. Then the server confirms our sequence number, so X plus 1. So this is the egg, and it also sends its own SYN, sequence number Y, and then we confirm the sequence number of Y plus 1. Why is this done? Because TCP wants to make sure that every packet is really regarded, none is lost, and even the first packet that we send out should be already detected as lost. So therefore we have to tell, this is in the traffic stream, we are currently at position X, and the server tells, okay, I acknowledge that, so please send me the next one. And now my real next packet comes, starting with X plus 1 as a first packet, and if it's not received, or I don't know, X plus 2000 comes, then the server would know, oh, something is missing because it was announced. The next packet that I expect has the numbering X plus 1. And if I receive X plus 2000, then I missed the things in between. So we need it for reliable communication. But what happens here, so if we send out a SYN message, then the server internally creates already, it knows, okay, this was the sequence number, this is my sequence number, maybe there's, yeah, that's already it, I think. It reserves some port to answer, port. So I now assume we just send a SYN packet and that's it. So we send just SYN packets and ignore all the rest. Then basically the potential, I mean, there's a little bit of state that the server reserves in its memory and waits until a timeout to give it free. Yeah. And on our side, we sent one message. We did not store anything, so 0. And on this side, I don't know, we created 1 kilobyte of data consumption, let's say. So how many messages do we have to send to fill up the available memory? It might not be sufficient with what? Yeah, let's say, why is this a good attack? Yeah, so this is actually I mean, we didn't have any costs in terms of storage. We caused, on the other side, a storage consumption, let's say 1 kilobyte. We had one message, and there was one message back, so that there we are equal. But the terms of asymmetry is here in the terms of memory consumption. So The server has to manage increasing number of half-open connections. It requires resources, at least memory. The attacker does not have to remember anything. And if we do that more and more, then typically the servers are also configured to have only a limited number of open TCP connections. I saw that myself. I mean, with HTTP servers that can be configured, with mail servers that can be configured. So you don't want to support 10,000 open connections. So they have a limit, and for a given time, until the timeout comes, you have reserved one of the spots, of the valuable spots that cannot be taken now by real customers. How would you stop that? How could we block it? So if you are the server, what would you do to identify this behavior? So this is A, this is the server. Can you identify the traffic? This is A is malicious, B is good. Yeah.
So if it's just A, then you can just see, oh, it's always the same address, then please block.
Yes, you can block it. I mean, you can say each customer can only open, I don't know, 3, 4, 5 open connections. That's it. That should be sufficient. So the attacker, what should the attacker do? Try to get a random send address when sending the SYN. How can this be done? So what's the easiest way to send a random to select a random send address? Yeah, we just spoof the IP address. We just claim that we have a different IP address. I mean, in software, the packet is created that is sent on the path. So what happens is in multi-hop communication, so if this is A, it can just, typically it should say, I'm A, I'm sending a message to B, if this is B. But A can also say, this is coming from Z, I'm just forwarding it. And this is coming, it's also for B. So it can create various, just claiming and spoofing this new IP addresses. Obfuscates the identity. And then it looks different, because then you get 1,000 individual TCP so connection establishments from 1,000 different sources. One of them might be a good one, and 999 are malicious. It's difficult to block, so you cannot know in advance. Maybe you put the timeout shorter, but then again, you might have slower valid clients. So the question is, what to do about it? So if we have this 1,000 requests, and all of them are reserving some, let's say, the sequence number on their side. So this is which sequence number they will use. This is the sequence number we will use. Maybe they are also in TCP. I mean, this window size, congestion window size, and there's this. There are actually 2 congestion windows. So one is about what is our internal state of how much we can send, and then receiver window, receive window. This is how much the recipient can receive. So basically all the information that you have in TCP in the header, sequence number, window sizes, your own sending speed, whatever you might have. This is the state that is creating 1 kilobyte, let's say, maybe also a little bit more. What can we do to avoid that we have the burden of these 1,000 individual connections that are going to be established? Maximum segment size as well. So the problem is we have to memorize it as a server in order to be able to deal with the corresponding partner, communication partner. What can we do? Any idea? So the simplest I mean, the simplest is, if the problem is that we have to store this information, let's find a way that we don't have to store this information. Who could store that information? Or where could we put this information in? So there's a message coming and we are sending something back. And we don't want to store the information at our local machine, at our server. Sorry? Buffer storage. Yeah, but where's the buffer located? Also in the server. No, I mean, we have to basically take all of this information and put it in the message and tell them, okay, here you have it. I don't remember everything. Next time you come up, please show me what I sent you. Sorry? That's one way, but actually we have to see what we can modify in this message that you sent out, where we can encode what is relevant for this communication. So let's see what is relevant for this communication. There's so here comes into play the syn cookies. Now that's a countermeasure. So this is a countermeasure. So we have the unique identifier of the connection with the IP address of client and server, port number, the time of the syn reception, yeah, so that we know when we have a timeout, maximum sequence size, initial sequence number of the far end, so that means the sender, the client. That we don't want to memorize. So what we do is we send it as a cookie to the client. And the next time the client connects to us, it has to provide us that cookie, that information piece again. What we need to do is all information must be put into this cookie, and we need to somehow verify that it came from us, so that the client cannot fake it or modify any information on that. So, so how can we do this without having a UTSP connection? Basically what we do is we identify where we can put this information in. And yeah, and basically the only thing that we can modify is the sequence number that we use in TCP. This is our free choice. This is typically either randomly taken, so there's still some room to use that. And these are 32 bits that we can use. So what we do is that we put in some kind of timestamp, that we put in the maximum sequence size, and we put in some cryptographic hash over the other information. So IP address, port numbers, and so on. Because the IP address and port numbers we will also get with when they reply to us. So we will be able to verify. We don't have to really store it, because every message coming from that client will contain this information. But we want to make sure that this was the old one. So basically that we have a hash over it, that we created this. So basically this is how we select our sequence number. So, and next time when a message arrives, so what happens? If that was the attacker, we answered them one message back and put all this in our sequence number. Case number 1, that was an attacker with a SYN attack. What happens if he doesn't reply? Nothing. No, nothing. I mean, he sent a message, we sent a message, we are even. There was no asymmetric resource consumption. Now, we look at the case that the valid customer comes in, and his message contains his IP address, our IP address, obviously his port, our port, his sequence number, and maximum signet size maybe. And now we can basically ask him, because this is our sequence number, so he has to send us back, he has to acknowledge our sequence number that we sent plus 1. So we can recreate what basically it was, we just subtract 1. And then we can verify, okay, is it really a valid cryptographic hash? I mean, here we can put in our kind of key so that only we can create it. So to verify that it was really from us, so it can be a hash over the data with a specific key, so that others cannot create this because they don't have the key. And then if the message comes in, this is the response. So basically this is the third message in the handshake. We can verify whether all previous steps have been correct. Actually, what you miss a little bit is the original sequence number is just assumed that it fits, but this is not so tragic. But by being able to only take the information of the second message, we can verify that the first 2 steps have happened, although we did not store any information related to it. So by this, the attacker loses its capability to store data on our machine at no cost for him. Okay. So this is with regard to SYN attacks. Has been also, quite frequently happening. And still the issue, we will have a look at, this amplification is not anymore there, and therefore the attack lost some of its appeal, some of its attractiveness. Still, what the attacker can do is to really hire lots of machines, A, B, C, D, and send lots of messages and try to consume other kind of resources of the server. And if you have, if the number of attackers multiplied with their bandwidth is higher of that of the server, then eventually the server will be unable to serve valid requests. But we lost the amplification. So basically, it's the amplification factor would allow us to reduce the required number of devices that you need to control to attack the server. Okay, let's have a look at another example. The Smurf attack. So in the past, routers forwarded directed broadcasts by default setting. A directed broadcast is an IP packet with a special destination address. So you send the IP packet, IP, A to A. And once it's arrived at the specific network, then it needed to be broadcasted. This must be valid to be a valid broadcast status for a subnetwork, which is not the sender's subnetwork. In addition, hosts have access to ICMP echo request packet that they receive to a broadcast. So what could be also done, so one of these broadcasts could be an echo request. Of this Internet Control Management Protocol. So what is an echo request? Do you know an application that uses that? Oops. It's a ping. Do you know the ping application? So what can you do if with this option? So there's this directed broadcast, meaning you send a message to a node in a subnet, and once that node receives the message, it has to broadcast it in a network, and the broadcast can be an echo request. How can you create a good denial of service attack with that? So what is the reaction of for a ping message that is received? So the ping that is received, so let's say this reaches, I mean, these are all different nodes that are reached, I don't know, B and C and D and E and so on. And they all receive this ping message, and then they have to reply with a pong. I mean, it's not really called pong, it's an echo reply. To which address? Hmm? No, it's. I think it's specified where to.
Destination to the sender.
To which sender? Yes.
Of the ping.
No, I think that's a good point to clarify. I mean, in the ping, there's not just the recipient who receives the ping, but there's also the destination named. And the pong goes to the destination. What is the destination? Who defines the destination? Who defines the destination for the echo reply? Yes? The sender, and actually this sender. Yeah. So what you can do is either if you're A and then say, are you A? Maybe just one IP packet in the name of A asking to reply back to him, and then all of these hundreds of machines will send him a message. So the question is, who's A? Was it spoofed or not? So basically what can happen is that if there's the malicious node, sorry, that's IP of the victim. So somebody spoofs in the name of the victim with this directed broadcast, telling A to broadcast this in a network, this echo request, and then all answers will then go to the victim. So that's the approach of the Smurf attack. Send an ICMP echo request packet as directed broadcast. Use the IP address of the victim as the sending address. And this is so-called reflection address because X sent something to someone and they answer to the victim. And in this case, it's also all these other nodes in the network. So a new approach, basically, X doesn't have to attack directly the victim, but it can ask others to send traffic and resource and consume resources of that victim. So it doesn't have to be directly. That's also nicer because now let's say the victim is attacked and receives magnitudes of messages for resource consumption. The victim knows that these machines were sending him messages, but that X is somewhere involved is not really visible. And so this is one benefit for the attacker. Another benefit is that the amplification factor is quite high because this is a network connecting to the victim. So many nodes, many end systems, many hosts, and it's much more attacking power. So what are the protections? Don't forward directed broadcast. So this is since then quite restrictively blocked because first the sender is not authenticated. Second, it is not a valid good approach to support this kind of amplification, to allow someone to send a message to all of the machines in your network. So the better way now, if you have a valid reason to do this, then you should be part of the network and send it yourself. Firewalls. So here might be a good firewall, and if you see as a firewall, you might have some kind of monitoring, or also we talked about what was this network intrusion detection system with the pig? Snort, yes. So if you have snort, and I mean, firewall works on the per packet level, but snort would count up how many ICMP messages you get, and let's say after 10 per second or so, then it would drop the packets. Yeah, and don't reply to ICMP packets received by broadcast. So any kind of management protocol directed to all should not be happening. It should be individual. So there's no good reason to have really broadcasts involved with management protocols. If you look at the elements, what ICMP allows us to do is basically tells you destination unreachable, redirecting message, echo request and echo reply. I mean, there's no reason to have any kind of information sent out to a group and they should answer in this terms of management protocol. So it doesn't make sense to send some kind of message such as destination unreachable to a whole network and not to individuals. Okay. Oh yeah, that's next good example. So let's talk about another way to amplify. And one way of amplification is to use DNS. DNS is a very interesting protocol because it's really one of the privileged protocols that are allowed, again, as we saw also in hotel lobbies, even if you didn't log into their Wi-Fi, this is typically always allowed, even if you cannot. This is so generic because it tells you where you find services for authentication, for this, for that. So DNS is often allowed. And what can be done is to spoof an IP address. So this is the attacker, and it just claims that it is the victim and sends out to a DNS server a request, and the answer is then quite large. So what is the benefit? The amplification. Here you send out, I don't know, 100 byte, and you might get 500 bytes or so. So by this, if both have 1 gigabit per second as bandwidth, it is sufficient to use 20% of the attacker to bring down the server. There are also other, real examples where this has been used. And the question is, how can you prevent this? So how can you prevent somebody, what enabled this attack? Maybe that's the question. What is the enabler of the attack? So what led to this amplification and reaching the victim all this traffic?
There's no authentication for DNS?
Yeah, that.
We would authenticate the sender. In this case, we would see that the IP address don't match, and then we wouldn't answer.
Yeah, that's right. And that's step number 1. That's right. And step number 2 is that this is quite large. I mean, without any additional, so you can ask basically the DNS server to send large packets. And the second question is to whom. So it has also some reasons. I mean, why is it possible to spoof the IP address in DNS? So why don't we use, what protocol do we use? TCP, UDP? What would you use? So for DNS, always in generic, but there are exceptions. UDP would be used because for TCP, so how quick is the DNS request over UDP? You send the DNS request over UDP, you get the response. With TCP, you establish the connection. Here you send a DNS. You get the response. So it's just quicker. And typically, you don't want to have an established connection for TCP because it's just one request that you send. So you want to send it away and then quickly receive the response. But one way would be to involve somehow to send a message back. So if you would use TCP, then the second step, the DNS query, would not be, so I mean, if I use the wrong IP address, so start with 5 instead of 1, then this message will not receive, I mean, the DNS query would not be sent out, so it cannot be spoofed. That would be one option. And the other options, we will have a look at next time. So basically, the next time we will look more into what else with DNS we can do, and then actually we are almost quite through. So DNS, proof of work, a little bit, and summary. And after that, we will look into the next topic, and this will deal with steganography. So how can we hide information in network traffic or in other kind of traffic? That will be also interesting. Yeah. I'm looking forward to see you on Friday. Oh no, Friday we don't have and on this Thursday there's